Hi guys, welcome back. In this example, we are going to model a system with a current source. Let's get into it. Okay, step one is listing the elements in the system. So again, I'm going to go after inertia, stiffness, friction, sources, and the number of ODs. Okay, so inertia, stiffness, friction, sources, and number of ODs. Okay, help me out here. How many inertia elements do we have in this system? Well, in electrical systems, your inertia element is your inductor. You see that? You do not have an inductor in this problem. So the number of inertia elements is in fact 0. Then I would go to the stiffness elements. If you guys remember, stiffness elements were the capacitors. I do have one capacitor. I'm going to put it here. And then I would have two resistors, R1 and R2. Yes? Okay. For this problem, my friction elements are R1 and R2. Since resistors are energy killers, they are my friction elements. The source here in this problem is the source of current, which is I input or IN. And at last, we need to comment on the number of ODs. How many ODs do you think that you would need for this system? Well, if you remember, with the number of energy storing elements, you end up with ODs, yes? And those energy storing elements were the inductors and capacitors. In this problem, I do not have an inductor. I have only one capacitor. So the number of ODEs would be 1. With that in mind, let's go to step 2. And find the dynamic variables. Okay, let's review again. Dynamic variables were either the current through the inductors or the voltage across the capacitors. I do not have an inductor in this problem, and I have only one capacitor. So the voltage across that capacitor would be my only dynamic variable. I'm going to go to step 3 now, and I will find the one differential equation that I need for this specific system to basically represent the dynamics of the system. So I would write the ODE for energy storing elements. Okay. Since I have one energy storing element, and that's the capacitor, I'm going to write down the equation for that capacitor. So C E dot C equals to IC. Okay. Now, looking at this problem, okay, IC is the current here that passes through the capacitor. Okay. At this point, I need to label these terms as good and not good. Yes. Again, guys, my good terms were voltages across the capacitors, my dynamic variables, and my sources. And if you guys remember, dynamic variables were either the voltage across the capacitors or current through the inductors, that we find them in step 2. Okay, let's go through this one. IC. What do you guys think about IC? Do you think that it's a good term or no? Well, you need to change your question. Is IC your dynamic variable? No. Is IC your source? No. Then IC is not a good term. Yes? E dot E. Do you think that E dot C is a good term? Well, EC is your dynamic variable, and E dot C is the time derivative of EC. So, in fact, it's a good term. And you guys know that C in this system is the capacitance. It's a constant number. And since it's a parameter, we don't care about it. So C is neither good nor bad. It's a constant number. Okay. Let's go to a step 4 now. And what we want to do in step 4 is in the equation smiley, let's call this equation as equation smiley. In the equation smiley, we want to rewrite the not good term, which is this troublemaker here, in terms of our good terms. So the good terms are dynamic variables and the sources. So in a way, we want to rewrite IC in terms of my dynamic variables and my sources. What are the tools that I can use? Well, there are 3 tools: KVL, KCL, and Ohm's law. So let's go into it. We want to rewrite the not good terms using KVL, KCL, and Ohm's law. Okay. So let me see what I can use here. KVL, KCL, and Ohm's law. Okay. By looking at this system, you see that I have 2 resistors here. Yes, R1 and R2. So basically, I can write, or I can use Ohm's law 2 times here. One for the voltage drop across R2, and second time for the voltage drop or rise across R1. Okay, so I can do Ohm's law twice in this problem. You already know that. Then let's go to KCL. Okay, for KCL, you need a node, a junction, a place that the wires in your system meet together, okay, and they're going to be joined to that node. You see that I have 2 nodes in this system, node A on the top and probably node B on the bottom. However, you guys note that if you write down the KCL for node A and multiply it by node B by -1, you will get the exact KCL at node B. Okay, so you really do not need to write down the KCL for both node A and B. Just one of them is enough. So you will have 1 KCL. Yes? And at last, you have 1 KVL. If you look at this, you can write down the KVL for this loop around here. Yes? Okay. In this problem, I assume that the direction of the currents are given to me as IN here, IC here, and I2 here. Yes? However, if these directions specifically for IC and I2 are not given to me, you guys can assume a current direction and follow your solution. If by any chance your currents come out as negative, it means that your first assumption on the direction of the current was wrong. Okay? That's all. So, let's summarize again. 1 KVL, 1 KCL, and 2 Ohm's laws. Okay? Now, let's go ahead and do the KVL first. I'm going to start walking on this circuit in the direction that I've shown you. Convention 1 says that when you go in the same direction of the current, the voltage across R2 drops. When you get to C, the capacitor, since you are moving against direction of the current IC, the voltage across the capacitor rises. Similarly, the voltage across ER1 rises because convention 1 says that if you go against the direction of the current, then the voltage rises. Yes? Okay. Now I'm going to go ahead here and I would write down the KVL. Negative ER2 plus EC plus ER1 equal to 0. Yes? Good. Okay. Now let's do the KCL. For the KCL, you have the summation of the currents that enters and leave the junction or the node is 0. Yes? Okay. So if you look at the node or junction A, you see that IN enters this node, so it's positive, and IC and I2 leave the node, so they are negative. Yes? So if you want to write down the KCL for that node, you will have IN positive, negative I2, negative IC equal to 0. Okay, and you see that, guys, here you clearly have IC. Yes, IC is something that you are looking for. And at last, you can use Ohm's law twice. The first time is ER1 equals to R1, the current that passes through R1, which is IC. The second one, ER2, is R2, the current that passes through R2, which is I2. Yes? Okay. So basically, you have these equations, okay? And in these equations, you notice that what you're looking for is rewriting IC in terms of your good terms, okay? So if you look at this equation, you see that by substituting ER1 here, okay, and ER2 here, you will get two equations. Yes, so you will have negative R2 I2 plus EC plus R1 IC equal to 0. Okay, and then the second equation is IN minus I2 minus IC equal to 0. You see that this is a system of equations where in this system of equation you have two unknowns. One of them is I2, the other one is IC. The rest of the things are either the inputs, okay, or your dynamic variables, which are the good things. Yes? So basically, you want to solve this system of equations for I2 and IC, okay, and basically find I2 and IC in terms of your good terms. One of the easiest way to solve this system of equations is by substitution, okay? So from the second equation here, you can find I2 as a function of IN and IC. So it's going to be I2 equals to IN minus IC, okay? And then substitute in the first equation here for I2 and solve it for IC. Yes? So if you do that, you will end up with negative R2 instead of I2. I'm just going to put it as IN minus IC plus EC plus R1 IC equal to 0. Yep. Okay. So just simply solve this one for IC. So what I'm going to do is I'm going to first distribute this R2 here and here, okay, and then gather the terms with IC together, okay, and then solve it. So it's going to be negative R2 IN, negative by negative would be positive, plus R2 IC plus EC plus R1 IC equal to 0. Yes? Okay, so do you guys agree that you can factor out IC from these equations? Then just factoring out IC from these two equations, you will have negative R2 IN plus R2 plus R1 IC plus EC equal to 0. Yes? And solving this equation for IC, solving for, let me just make it a little bit nicer here, solving for IC, you will have IC equal to basically R2 IN minus EC over R1 plus R2. Yeah, okay. And this is the equation that you wanted to find. Okay, look at this equation. In this equation, you see that R1 and R2 are constant numbers. So these two guys are constant numbers. We don't care about them. Okay. R2 is also a constant number. I don't care about this either. Okay. Then you will have two dynamic terms here. Okay. Actually, one dynamic term and one input. IN is a good term. EC is a good term since it's your dynamic variable. So you were able to find IC in terms of your good terms. Okay. Now, let's go back to the original equation smiley here. Okay. You see that the only thing that you need to do is you need to substitute IC from here, which I'm going to call it as equation 1 in that equation. Okay, a smiley. So let me just copy and paste this IC in that equation. So substituting equation 1 in equation smiley, you will end up with, let me just rewrite equation smiley, C E dot C equals to IC, okay? And instead of IC, I'm just gonna substitute from equation 1. Yes, okay. Okay, so let's make this one a little bit nicer. I'm gonna get rid of IC here since I substituted the value for it, okay? And at this point, what I can do is I can multiply both hand side of this equation by the denominator here to just get rid of the denominator. Yes, so it's gonna be R1 plus R2 multiplied by C E dot C equals to R2 IN minus EC. Yes, and then at this point, I can gather all the inputs on one side, okay, and all the dynamic terms to the other side, check for the signs. If the signs match, I can box this equation. Yes, okay, so this is gonna be R1 plus R2 multiplied by C E dot C plus EC equals to R2 IN. Okay, on the left hand side of this equation, I have a family of EC. Within that family, I have two members, EC and EC dot. There are no sign mismatches within that family members. Okay, so I can safely box this equation and report it as my final answer.